Hello, and welcome to reInvent, and welcome to Running Lean Architectures, how to optimize for cost efficiency. And thank you very much for choosing this session and for coming here so late in the day and not going to the pub crawl. So this is really a big honor for you to have you here. So you're actually the reason I'm coming to reInvent every year. This is the 6th year I'm giving this talk. And every year, my goal in this talk is to help you save so much money that you can easily pay for your next reInvent trip. And actually, I'm very glad to have JC and Patrick here on stage with me. They were actually here last year, attended this session, followed some best practices, and now they're here on stage presenting about their experience. So if you follow this session and implement those best practices, you could be here next year on this stage. So my name is Konstantin Gonzalez. I'm a Principal Solutions Architect with AWS in Germany. And let's get started, because there's a lot of stuff to cover now. So what are you going to get out of this session? First, we're going to cover some best practices on how to lower your AWS bill. This is why you're here. But it will turn out that these best practices can also help you build a more scalable, more robust, and more dynamic architecture. So it's going to be a win-win. This is not a trade-off. This is actually a win across the board. And it will also show you how to create more time to innovate. You will save money and time, and that will help you build better architectures, better services for your users. We're going to discuss some real-world customer examples, and some of them are really easy to implement. So ideally, you would leave this session, fire up the AWS Console app on your phone, and start saving money. Even if you don't do anything, we work really hard to lower our prices. So this is our philosophy here. Whenever we reduce our prices, more customers end up using the AWS platform. And that means we see more AWS usage, which helps us build more infrastructure, which helps us enjoy better economies of scale, which leads to lower infrastructure costs, and that helps us reduce our prices even more. So that vicious cycle, this flywheel, is actually accelerated by an ever-growing community of AWS users, the bigger global footprint, new features and new services, and the amount of innovation we can put on top of that cost savings into our platform to be more and more efficient. And over time, we were able to reduce our prices 67 times since AWS started in 2006. Now, AWS is for builders, and you're all builders here in this room. And as a builder, you build it, and you run it. You've probably heard that before. But the other thing is, you also optimize it. And the thing is that in the past, when we used to work with hardware, architectures were hard to change. You built something, and then you were stuck with it for 3 to 5 years. Now in the cloud, you can change architecture all the time. So you can optimize and optimize and optimize and enjoy more savings and improve your architecture. So please do that. Because as an architect, your biggest strength really is architecture flexibility. Don't worry, I'm not going to do this pose here. But the point is, enjoy and also take advantage of the flexibility you have on AWS. So when you want to save money, the main goal here is to avoid wasteful cycles. And by wasteful cycles, I mean things like unnecessary resources or idling resources. Could be EC2 instances that are not fully utilized, or repetitive work. If you catch yourself doing the same stuff all over again, maybe there's an opportunity to be more efficient here. So let's take a quick look at the overall process. And it always starts with measuring cost in this case, right? You measure something, and then you come up with ideas on how to improve the architecture. You architect, and then you build and implement those ideas. And after you realize a couple of wins, you can start from scratch. You can start measuring again, coming up with new ideas, and it's an ever-growing cycle here. So let's start with the measuring bit. And a good way to start is by checking your AWS Billing Dashboard. You probably know that Billing Dashboard, and it'll give you a quick glance on your cost. And one thing you can do is you can check out the AWS budget part of the dashboard. So just find the AWS budget piece on the left side of the dashboard. And this allows you to set up a budget, a monthly budget, and you can create notifications so that you'll actually receive emails when you're reaching 80% of your budget. So this gives you better control over your spending. And then you can dive deeper using the AWS Cost Explorer, because the Cost Explorer gives you the data that you can slice and dice based on regions, based on services, based on instance types, based on many different dimensions. So you can analyze where are the big spots you're spending something with and where could you start optimizing. So after measuring, let's take a look at some architecture best practices here. And the first thing, if you only take one thing away from this talk, is turn off unused instances. It sounds super obvious, but you wouldn't believe how many unused instances are running today where people can save money. Those unused instances could be developer instances, it could be test instances, could be training instances, and think about it. You start a test instance, you test something, you're fine, and then you go about your work, and you forget about the test instance. Very easy to do. Or maybe you're running a training and don't shut down the instances because you might need them tomorrow, and then those instances are running. So try to remind yourself of turning off those unused instances. You can simply do the instance stop thing, and the instance is not going to vanish. It's just stopped, and you can restart it again next morning. And one thing is, we recently introduced this for databases too. So if you're running a database on RDS, you can turn off that database again and then turn it off the next morning. This used to be not possible, and after, a couple months ago, we introduced this as a feature. The other thing is you can even turn off whole architecture setups. If you're using any kind of automation like CloudFormation or Terraform or some other way of scripting your architecture, you can set up a really big architecture that you're setting up as a test or as a training architecture, and when you don't need it anymore, you shut it down completely with all of its resources, and then you start it again. Main point here is, in the cloud, resources are really disposable, and don't get attached to your resources too much. Simply get rid of them when you don't need them, and then you can start saving. So here's an example from a customer. On this graph, the y-axis shows you the amount of instances this customer is using over time, which is the x-axis. And you can see how the week plays out over time. You can see where Monday starts. You can see how Friday introduces the weekend, and then this customer is shutting down a lot of instances. You can even make out the end of the vacation season here. And in this case, this customer is saving 35% of their EC2 bill just by turning off unused instances. Now, after doing this for a couple of months or so, you'll probably become or feel bored. So you should start automating stuff. So this is probably the other big thing to take away from this talk. Automate everything. And you can automate the whole start-stop thing with SDKs, with the command line interface, with CloudFormation, other tools here. Or you can use the EC2 autoscaling mechanism. Who uses autoscaling already? Okay, a couple people, but still not enough. Autoscaling is really a very easy way to automate your infrastructure. So how does it work? Well, autoscaling uses Amazon CloudWatch to collect metrics about your running infrastructure, such as latency or CPU or other metrics. And it can use those metrics to get a feel about how much infrastructure you really need. And the other component of autoscaling is it automates the instance provisioning bit. So you can set up a launch configuration where you tell it everything you need to know to launch a new instance. And by combining these two things, autoscaling can adjust the number of instances that are running in your architecture automatically. So you simply set up minimum and maximum number of instances. You hook it up to a measure that helps you understand the load, and then it does its thing automatically. And you get 3 wins. Win number 1 is you get automatic capacity management. So autoscaling will automatically make sure that you get just the right amount of instances running in your architecture. Second win is you also get a more reliable architecture because autoscaling will automatically replace any broken instances. And finally, you will save money because if you are running too many instances and there's not enough load to justify those instances, autoscaling will automatically terminate those overflow instances. So there are 3 easy steps to set this up. Step number 1 is to set up the launch configuration. This is basically a JSON or a way of collecting all of the necessary data that you need to launch a new instance. And then you set up the actual auto-scaling configuration with minimum and maximum and where the load balancers or other pieces that are relevant to auto-scaling to making a thing. And then you can start saving and watch CloudWatch as auto-scaling automatically provisions your infrastructure. In this graph, we can see the number of instances that are provisioned. You can see how over the course of a day, it's increasing load and it's increasing the number of instances. And as the day ends, it will shut down instances and saving you automatic money. And the key takeaway here is, in the old IT, we used to love our machines. We treated our machines like pets. We gave them names, and we treated them like individual servers. Every server was its own individual thing. We did a lot of manual administration. And that also could lead to configuration drift. I mean, you know, you log into the instance, you fix something, and many times this doesn't get documented. So by doing all that manual administration, there's also potential for error, which creates a lot of work, actually. So in the new IT, in the automated world of the cloud, you should think about your instances and your EC2 resources like cattle. I know these are not real cattle, these are actually sheep, but I like this picture better. So the point is, try to make them highly standardized, right? Every instance should look the same and should be fully automated, which helps you because it carries less error potential, right? If everything is automated, less potential for error, which means less work to do and more efficiency, which also translates into bigger savings. You can use auto-scaling also for things like DynamoDB. So DynamoDB comes with its own auto-scaling engine. And as you know, DynamoDB is built by the amount of capacity units that you assign to your database tables on DynamoDB. And you can program DynamoDB to adjust those capacity units automatically for you based on demand. And this is how it looks like. The blue line is the demand line, and the red line is the amount of capacity units that DynamoDB auto-scaling automatically assigned to the tables. Okay, these were the basics. Let's start with something a little bit more sophisticated. So who is using spot instances today? A couple people? Great. Let me tell you a little bit about spot instances. So what are spot instances? As you probably know, AWS manages a lot of hardware across many, many data centers all over the world. And we have to keep a lot of these instances waiting until you hit the launch instance button or until your architecture starts this automatically. So these instances are sitting there doing nothing, waiting to be started by the next customer. So what do? We offer these instances at a steep discount. So these spare capacity instances can be bought at very steep discounts. And we create the price, or we find the price based on supply and demand, right? So if there's many people who need those spot instances and put in those spot requests and not a lot of supply, then the price will be higher. But if there's a lot of supply and not many people asking for spot instances, the price will be very, very low. There is one downside, and the downside is if we need those instances back because we have customers launching instances on demand, then we will take them back from you. But there's going to be a 2 minutes notice, and you can program spot instances to hibernate themselves so that they are not lost. They will be restarted again when the price goes low enough. So this is how spot instances looked like about a year ago. So this is a graph that tells you about the price on the spot instance market, and the different colors are different availability zones. And as you can see, there were very large spikes. Those spikes could occasionally be even greater than on demand because people tended to outbid themselves on the spot market. And this led to very unpredictable behavior and created a lot of uncertainty. It was complex to architect around that. Now, spot instances look a lot better. I mean, the prices here are a lot lower. You don't see any spikes anymore. This is very smooth pricing now, very predictable. And now you can really depend on spot instances. And the price is always going to be lower than on demand. And that makes it easy to manage and easy to work into your architecture setup. We also created the EC2 Spot Advisor. It will take the historical pricing of the spot instances and give you a forecast about what is the probability of losing an instance on spot. And that can help you plan really nicely. And there's another tool you can use, which is EC2 Spot Fleet, which helps you manage large fleets of Spot instances and using them for things like batch. So let's talk to a real Spot customer here. And I'd like to introduce you to JC and Patrick. And they will tell you their story on how they optimized their spending on AWS and how they found Spot instances and introduced them into their architecture.
Thank you, Konstantin. So good evening, everybody. I'm very happy to be here today to talk to you about the cost optimization work that we have done at Expedia. So as it was announced last year right here at reInvent, we at Expedia are all in on AWS. The challenge we face was the following. How can we move quickly but safely to the cloud? One strategy that we adopted is called move and tune. In this two-phase approach, we started by moving our application as is without any re-architecture. And then we started tuning phase, measuring and finding what were the optimal changes for improvement. Our experience showed us that the biggest return that we got from cost optimization work was the re-architecture that came up with those tuning phases. Tonight, we are here to share with you the story of two teams at Expedia that walk that path of move and tune. I'll invite Patrick to talk to you about his journey in the content systems team.
Thank you, Jean-Cédric. I'm also really happy to be here to share our story. I'm a member of the content system team. So when we talk about content in Expedia, we talk about things like media, properties, description, paragraph about hotels, room, and bookable products. My team is responsible from one service, the content multiple service, but one of them is the content distribution service, which is the service that returns localized content to users, like for one of the users is the hotel, Expedia hotel search page. And so you see the amount of content that we have. If I have to break it down by hotel, I would say that it is around like 100 kilobytes of content for one hotel for one language. Most of the time, like our clients, they call our service with 1 or 2 languages and with up to 70 hotels per request. So that's a lot of content. In 2016, we used to have our application running in the data center. The architecture for this application was already 5 years old. It has been designed at a time where the number of hotels was five times less, and the content for each hotel was less too. So it has been built around like an in-memory grid. We used to have like a larger object that contains like all the content for all like the localization for one hotel. So this object was huge, and the full dataset was partitioned within the in-memory grid cluster. So one issue that we had, like one cluster was only able to handle something like 400 TPS, and the service received around 2,000 TPS at that time. So what happened is that we had to add more and more clusters. We start with 2 clusters, and we end up with 10. As you can imagine, managing 10 clusters of that size is not an easy task. It means like a lot of support for the team. Like we need to deploy, monitor, and many times we had to reboot cluster because the performance was not good enough. On top of that, like those clusters, they were the hardware for the cluster. It was expensive, and managing the cluster was expensive too. So you may wonder why we were still on this architecture given all those issues. Truth is that it was really hard to test new ideas. It was hard to get the required hardware to test new architecture. And when we were testing like different ideas in test, our stress environment did not show the same result of what we were seeing in prod, making trying new things like risky, if you want. So then we had the opportunity to move to the cloud. So the initial idea was to do a lift and shift, meaning that we'll bring our AV stack up to the cloud. And we did that, like we had a 1 month time box. And at the end of the month, like it was working. Like we have been able to lift our old stack or AV stack up to the cloud. It was working, but it was like the cost of the stack was really expensive in the cloud. Two main issues, like one of them is that we did not enforce compression header. So as the content is so big, and you have to pay for when you transfer like data over like different networks. So that price was really expensive. The other issue is that the in-memory data grid, it was using expensive EC2 instances. So that like the cost for that was really like important. So after less than a month, we just stopped the experiment because it was just too expensive. With this new learning, like it was now possible for the team to decide something that makes much more sense in the cloud. So we worked like on like a more native design. Basically, it's kind of simple. Like we just split the big objects that we have that contain all the content in all languages and into smaller objects for each languages. We store that into Elastic Cache. And we use RDS, Aura in our case, as a second layer cache. So what happens is the application receives the request. Depending on what is requested in the filter and the hotel requested, we get the content from memcached. If anything is missing, then we fall back on Aura. The application assemble the response and do some additional filtering and just return the response. So yes, like I would say that the initial version was not that perfect, that the response time was not that improved. But with few iterations, like we have been able to improve that, and now we have like an application that suits our needs. So for us, like a great improvement when we move to the cloud is that we have been able to work on our architecture, and we have been able to simplify this architecture. So the way I'm seeing this is that a simpler architecture is easier to maintain, and there will be less bug with such an architecture. Sorry. The other improvement is that we have been able to save on costs. So the stack in AWS costs 72% less than the evaluated cost of the same stack in the data center. So that's a big improvement. The service is, So one of the reasons for that is now we fix the issue about the data compression. We force our client to use compression header, so the cost for the traffic is not as much. And we use auto-scaling based on CPU to make sure that we always use the right number of instances. So that's a big improvement over what we have in the data center before, because in the data center, you need to have enough hardware to support the maximum load that you can possibly receive. So in the cloud, you just pay for the instance that you need. The great pleasure for the team is to have a product that is easier to support, that is much more stable. The TP99 is 6 times better than what it used to be, and it's really stable over time. Those improvements, they have been noticed by our service consumer. Some of them, they used to call our application only once a day, and like once a day for each hotel, and then they used to cache the data. So now they drop their caching, and they get fresh content every time they call our system. So with those changes, like we now have 3 times more traffic than what we used to have like 2 years ago. The flexibility of the environment makes it possible to to try new ideas. So if a developer has an idea, you can just try it, and if it is better, we'll measure it, and then if it is really better, then we are going to use that in prod. The move to the AWS has been a success, but we still have service consumers that are running in the data center. And we need to be present in the same network as them. So what we did is we took our simplifier architecture and we did the lift and shift back to the data center. So now we have one code base that runs in all environments. So that's what I want to share about our move to AWS. So now, as we say in the north, I will pass the puck to Jean-Cédric so we can talk about the challenge that he had with the geography team.
Thank you, Patrick.
Thank you.
So quite a journey for the content team, so to the cloud and back again. So what is geography? Geography, it's everywhere, it's all around us. At Expedia, our geography platform is involved in the majority of the business use cases. For example, when you search for hotels on Expedia, our service gets called to find where is your destination on the planet, what are the hotels over there, and also what's around, like airports, neighborhood, point of interest. All that things that are driving your shopping experience. Because it is so critical for the business, we operate in multiple AWS regions and also in our own data center. This allows us to be close to our clients and to meet our fast SLA. Now, setting the ground for our cloud migration. So when we decided to move to the cloud, we agreed that we would keep the same code base and deploy the same thing everywhere. And we also made sure that we would leverage all that commodity, those commodity resources at our disposal in the cloud. All our service components are fully compatible with AWS, so our lift and shift approach was pretty easy to do. But one key decision that we made was to embrace DevOps and really to automate everything. We invested our time in infrastructure as code with CloudFormation, and we came up with a pipeline that allows us now to have predictable and consistent result. This full ownership model quickly allowed us to test quickly new functionality in the cloud and allowed us also to try out new engineering techniques like chaos testing. It also provided us with great visibility on a new reality when you operate in the cloud, cost awareness. So now let's look at what our architecture looked like once we moved to the cloud. Looked like any typical REST service. Load balancer up front, an auto-scaling group that allows us to run in multiple availability zones, database at the back, and some memcached nodes for performance purposes. Now, before we moved to the cloud, we knew we had some limitations with this architecture. But because we were operating in a static environment in our own data center, we were able to mitigate the situation. Moving to the cloud forced us to do something about it. We had to work on our robustness and resiliency so that we could improve. And also, what we realized quickly is that operating those multiple terabytes memcached nodes on the Elasticache is quite expensive. So this started our tuning phase. And we decided to add a second layer of caching in our architecture. This new solution with persisted and replicated state would allow us to be more resilient. Having 2 layers of cache would provide us the lever to fine-tune the balance between fast access and capacity. And we also believe that we could be better to be more cost-effective and save a few bucks along the way. Some objectives with our project was, it's good to improve on your implementation, but we needed to keep it fast without any negative impact on our clients. We have a background process that is constantly updating our cache for fresh data. So we needed something that would support this write-heavy use case on our cache. And because of the nature of our service, we need also something that would support a variety of payload sizes. To implement our solution, we tested out a few things. We evaluated AWS services like S3, Aurora, and Dynamodb, but we came up to the conclusion that the best solution for us, both from a cost and an engineering perspective, was to run our own Cassandra clusters. EC2 provides all the resources and flexibility to do so, and those specialized i3 instances with their super fast SSD drive provided all the I/O capacity we needed. So here it was, Cassandra as our second layer, and by doing so, we also changed the role of memcached. It became our first layer. We reduced its capacity, and we're now only keeping the latest entries in there. The results were pretty good. We were able to reduce our cost by over $1 million per year just for the operation of our caching solution, while increasing the capacity by 4x. That's a little bit more than a few bucks. And all this without any negative impact on our clients. At that point, the team decided that we should do another spin, another optimization cycle, to see if we could get a little bit more out of this solution. And it's then that we realized that we were using memcached, an in-memory cache that provides single-digit latency to transmit multiple megabytes of payloads over the network. That was not a very clever decision. So we decided to put a hard limit on what we put in this first layer, to only keep what is less than 1 megabyte. Our final test not only indicated that we were still as fast as before in general, but now we were 25% faster on big payloads. Needless to say that was a pretty successful project for the Geo team. It was available because AWS provides all that flexibility, but also all that automation that we worked on during our migration paid off in making that possible. Now let's change gears and talk about another thing that we are using in the Geo team to save money: Spot instances. So like Constantine showed us, Spot is a great way to save money, but it comes with some risk. Before we started to use Spot, we had to change our philosophy, to change our mind, and take for granted that we would lose those instances. So to account for this, we figured out some characteristics that our services or processes, regardless if they are stateless, stateful, or background jobs, would need to have to support Spot. And to mitigate the risk of Spot, we came up with some simple strategy. The first one is called fire and forget. As its name implies, we simply configure our auto-scaling group to launch Spot instances, and we simply hope that nothing will happen. So, for example, we use this process, this technique, on this background job that is updating our cache, as well as daily data jobs that we have that generates feeds for our partners. We have no mitigation in place, so if we lose our instances, we simply wait for them to come back. And this is fine because those are not mission critical. But by being careful, clever, and by understanding the rules of the game, now we can take decisions to minimize the probability of losing instances. To maximize our supply, we decided to only use previous generation instances. So when you all recently migrated to those brand new R5 and M5, guess what you left behind? A big pool of available instances for us to use. And to avoid any issue with the Spot price, we simply did what AWS recommend, and we always bid the on-demand price. Using this strategy, we never lost an instance in 2 years. But sometimes this strategy is not applicable because you want to use this specialized type of instance that has more dynamic forces of supply and demand. And then we came up with another strategy we call free-falling with a parachute. In this strategy, we run our instances on Spot, but we have a fallback. We have a manual trigger that we can use to bring back our instances to on-demand if needed. 2 key characteristics to use this strategy is that the service or process that you're running that on must be able to sustain failure or interruption without any immediate intervention. Also, another important point is that even though the trigger is manual, the recovery mechanism must be fully automated for consistent result. So imagine that you're jumping out of that plane. At the moment that you decide to pull that trigger on the parachute, you don't want to see a label popping up that says assembly required. So remember those Cassandra clusters? So we decided to apply this strategy on them and run part of our clusters on Spot to further reduce our cost of operation. Cassandra is fully compatible with this strategy because it is resilient by design, and it can run with some node failure. The way we did it is that for each Cassandra node, we have an auto-scaling group backed with a pair of launch configuration that allow us to move back and forth between Spot and on-demand prices. When we lose an instance, whether it comes back on Spot or on-demand if we use our fallback, we have automation in place that detects the recovery mode, makes the node joins back the cluster, and automatically resync all the data. So what did we get at the end of all that work that we've done? So obviously, by running over the quarter of all our instance hours on Spot, now it comes the savings with it. And that allows us to reinvest all that money in other projects. But the biggest reward we got is that all the hard work that we have done to safely use Spot made us stronger. Working out this resiliency muscle gave us a big boost so that our services are closer to this ideal of bending but not breaking. We are now operating in a state where losing instances, whether is it Spot or AWS maintenance or health check failure, is part of our day-to-day routine. But most importantly, now we have a method, we have a pattern that we can reapply across the organization to be more resilient and to save money at scale. So all that work was pretty fun to do, to be honest. But none of this really matters if you are not being careful about your overall cloud spending. Forgotten resources or idle instances can eat up all your savings, and that could be quite frustrating. So this is why at Expedia, we have put in place some cloud cost governance practices. Our program evolves into around 3 key pillars. The first point is we need good metrics. We provide to all the teams at Expedia some Kibana dashboards that allow them to deep dive in any dimension. The second point, we need to set targets. So on a regular basis, we agree with finance on some forecast, and each team is accountable to stick to those targets. The most important point of all this is that all this data is available to anybody for full visibility and transparency. This really enables collaboration between teams to find what are the best things that we can do to save money and to track our costs. So to conclude, the big lessons that I've learned during all my journey is that, first, we need to treat cost as a limited resources during all the phases of the software lifecycle. The same thing we're doing today with CPU, memory, and network bandwidth. And the other lesson is a counterexample. So never, ever reduce your capacity to be redundant or resilient just for the sake of saving money. Always be safe first, and then you optimize. So on this, we'll go back to Constantine and learn more tips and tricks on how to save money on AWS. Thank you.
Thank you, JC. Wow, $1 million saved. Wow, you could have brought your whole family to Las Vegas this time. Yeah. So think about some use cases where you can apply Spot instances on your own. Containerized workloads are great because containers should be stateless, and that makes it easier to run on Spot. Big data is a great application spot for Spot, Elastic MapReduce, even CI/CD pipelines, or any kind of high-performance computing, including financial simulation or transcoding. These are all great ways of using Spot instances. Check out the Spot homepage And just a few weeks ago, I think 2 weeks ago or so, we introduced a new feature for autoscaling so that you can now mix different purchasing models like spot and on-demand inside the same autoscaling group. And you can also mix different instance types, so you can take advantage of bigger pools of available instances by mixing different instance types. So now you can get the free-falling with a parachute mechanism built in with autoscaling in a very easy-to-use way. But many people say, okay, we talked about scaling, but what if my application only needs one single instance? Or what if I have many applications and each of them uses a single instance and I'm not able to scale up and down that much? This is where you can leverage containers to consolidate those mini applications into fewer servers. So if you have those small applications that are only using small percentages of EC2 instances, you can containerize them, and then you can run those same applications on a smaller number of actual EC2 instances by using containers as a consolidation mechanism. So here's how this works. First, you should make your applications stateless, which enables them to be more mobile, more flexible. And then you can run them on a container platform of your choice. It could be ECS, it could be EKS, it could be Fargate. And then you can start saving by adding them on or using them on spot instances. So you can get like two different kinds of savings. First, by consolidation, and second, by using them on spot. And now, serverless is all the rage, right? Who's using Lambda in this room? A couple people here. So Lambda is a great way of saving money. It also gives you automatic scaling. It gives you automatic provisioning. And there's no need to manage anything, so it's also very easy to use. You just bring your code, and Lambda does the rest. The billing works like this. You get 1 million free requests per month, and then you just pay a very small amount per request, and the runtime is built in 100 millisecond increments. And as a rule of thumb, if you're looking at an application and it uses 40% of an EC2 instance, you can instantly save money by simply porting that application to a Lambda execution model. So the key thing to remember about serverless here is you never pay for idle, which is great. But there's a small catch here. If you do idle inside of a function, like if you're intentionally waiting inside a function, then you still pay. So you should really avoid wait cycles in your application. So here's an example where those wait cycles could be. This is a typical Lambda function. It sends a couple of HTTP requests. Maybe it's collecting some data. So it sends out an HTTP GET request, and then it waits for this response, and then it sends the second request, and it waits for each response. Each HTTP request could be an API call, or it could be real data that's flowing here. And at the end of the whole thing, Lambda does its thing. You compute something, and then you deliver a result. As an example, this is one function that I use in one of my personal setups. This is a function that collects data from different RSS feeds, and then it creates a combined feed and delivers it to some next stage here. And over time, this function was taking longer and longer and longer to execute because over time, more news piled up and stuff like that. And this actually happened during my vacation until the total runtime hit the ceiling of 5 minutes, and then my function failed because it was forcibly terminated by the Lambda system. Now, I had to pay for the full 5 minutes, and then the function still failed. That wasn't funny, especially during my vacation, because I got that email from CloudWatch telling me, your function failed, right? So what did I do? I actually followed my own advice, because 1 year earlier, during the same talk, I told people to avoid these things, right? So I rewrote my code, and it actually took me just 1 hour to do that. And I placed my function calls, or the HTTP GET requests, I put them into multi-threaded code. So now the execution looks like this. I do get, very fast because they are multi-threaded. And the waiting happens in parallel, so that the total time now becomes a lot shorter, and I'm spending a lot more time being productive in my code and a lot less time waiting for HTTP requests. So the trick here is you can use parallelization through multithreading, or you can use event-driven languages like Node.js to get rid of wait cycles that can accumulate as a result of network latency or network lag or other I/O or other wait stuff that you can't really avoid. So you can parallelize around that and save time on Lambda. In my case, I was able to save 60% of my execution time simply by introducing multithreading into my Lambda function here. The other thing to avoid is intentional waiting by using things like a sleep function of your operating system. So in this case, you have a Lambda function which starts the job, and then it sleeps for 10 seconds, and then it asks, is the job done yet? So it's a function that's waiting. Very common pattern, right? You could start an Elastic MapReduce job, and then you wait until the job is complete, or you're doing a complex database request, and then you wait until the request is done. And you can avoid these things by letting something like AWS Step Functions do the waiting for you. So AWS Step Functions is a very easy service that you can use to implement workflows. And in this case, you can set up a Step Functions execution flow where the job submission is at the beginning, and then you do the waiting as part of Step Functions. And the great thing is that inside Step Functions as a workflow engine, the waiting is for free. So you don't pay for the wait time inside a Step Functions execution flow. So you might think, okay, Konstantin, you're optimizing here on the seconds. Is it really worth it? Does it really save you so much? Well, it adds up over time, or it adds up over transactions. In this case, Coca-Cola, for instance, they had a system where for each bottle that they sold through their vending machines, they updated a database with the loyalty points that the customer was collecting as a result of buying those bottles, right? And the Lambda function initially sent the update request to the database, and then the database kicked off a backend process to update the loyalty points. And the Lambda function waited 90 seconds, and then it asked the process, okay, are we done here with the loyalty thing? Is everything okay? And then it would do its thing. And in this case, the customer replaced the Lambda function with a very simple step functions approach. Update the points, wait 90 seconds inside step functions, and then check if everything went through. So Coca-Cola now is saving 90 seconds Lambda execution time for every bottle they sell in their vending machines. That adds up to quite a lot of savings here. So the next thing is, I always wanted to have hamsters in my presentations. So what does this hamster do? What are hamsters really good at? Well, caching, right? Those hamsters, they gobble up all that food, and they store the food in those cute little cheeks here. So what should we do? Well, you should be caching like hamsters. And Patrick and JC, they already used some caching in their architectures. And the thing is, caching means that you do the expensive stuff only once, and then you can reuse it as many times as possible. This is a great trick to save money, and it also accelerates your architecture a lot. And the reason is that memory tends to be a lot cheaper and faster than CPU cycles. And you can cache at every level of your application. So this is a typical web application. You can cache on the edge. You can cache on the web tier. You can cache on the application tier. You can cache on the database tier. And you can place caches all over the place. And every time you introduce a new cache into a layer, you will see more savings, and you will see faster execution times. Because when you cache in your application, whatever is sitting behind the cache can be downsized because there's less stuff to do as you can cache more and more stuff. And the easiest way to introduce caching is by using Amazon CloudFront, which is a cache network that sits on the world, all over the world, and that you can place very easily in front of your application. In fact, I have a customer who had a problem. They had a performance problem with their web application, and it was still running on premises, right? So I had a workshop with them and told them, okay, why don't you put this into the cloud? And yeah, but we were worried about downtime. Okay, so use CloudFront, and it will cache, and it will also gracefully give you the opportunity to move behind the cache and everything. So they put CloudFront on top of that, and they saved a lot of resources, even on premises, and that they didn't migrate at all, just out of laziness. So they actually migrated a year later, but it bought them a lot of time, actually, because they were able to manage a lot higher load with the limited resources they had. So you can use CloudFront in front of your application very easily. And then you can use things like Amazon Elasticache, like Expedia, and introduce it into your application. It's a very easy to use in-memory key value store, very high performance, and it supports 2 different engines. Very simple to use Memcached engine and a more sophisticated Redis engine. And it's fully managed, so you don't have anything to do. You just start the Elasticache service, and then you start caching. It's very highly available and reliable, and we work hard to make it very robust, so you'll get actually a very robust service out of that. And it's easy to implement. If you have a typical application here, which is talking to a database, you simply put the Elasticache layer in the middle, and you modify the application to first ask the cache, hey, have you seen this request before? And the cache can say yes, and then you save money and you save time, or the cache says, no, I haven't seen that before, and then you go to the database. And after computing the result in the database, you simply store it in the cache so you can reuse it later. Here's an effect on what you might see here. So this is a customer of mine. Actually, he was on stage last year to present this. And they introduced a caching layer in front of their DynamoDB table, and they were able to save, in the very first attempt, 3,000 reads per second. And then as they introduced this to more and more tables, overall they saved 20,000 reads per second, which allowed them to downsize the table capacity units and save a lot of money here. And this customer learned a very powerful lesson. You can also cache nothing. Because at first they didn't realize that they had many requests against their database where the database responded with an empty result set. The database simply said, I don't have an answer for you. Go away. And then they started caching those negative answers. So they cached all those empty sets. They even cached errors from the database. And that saved them so much because now they went from a hit ratio from 25 to 30% to 89 to 95% hit ratio just by caching negative results. So think about caching really everything. And then they started playing with Dynamodb Accelerator, which is an automatic caching layer that Dynamodb has built in since about a year now. And this is how the performance looks like without the Dynamodb Accelerator. So you see an average of 5 milliseconds or 6 milliseconds response time and consistent performance. This is what you get with Dynamodb. People love the consistent performance here. There's no warming phase. We'll get back to that in a minute. And you also get detailed metrics per request, which is a great feature for debugging. And then they switched on the Dynamodb Accelerator feature, or DAX. And the response time went down dramatically to about 1/10. Now they're seeing 400 to 450 microseconds in latency from Dynamodb. Drastic acceleration here. Very, very consistent performance. Even the consistency improved a lot here. But they need to introduce a warming phase, of course, right? You need to fill up that cache before you can really leverage its performance here. And DAX doesn't support detailed metrics on a per request level. So in this case, do the debugging first, and once the application runs nicely, then you can switch on the caching feature, and then you can start saving money because you can now provision a lot less capacity units, and you will have a much faster application overall. So finally, the last best practice I would like to introduce to you is to avoid unnecessary work. And it's good to be lazy here, right? So what do I mean by this? Well, leverage as many existing services as you can. Avoid reinventing the wheel, which means that if you want to run a database, try first to run those databases that AWS provides as a managed service, like RDS, DynamoDB, Redshift, and other databases that are already there, and they're already managed for you. You don't have to invest time and money and effort into managing that stuff. Same thing goes for stuff like Elasticache, Elasticsearch, sorry, or messaging using SNS, Simple Notification Service, or even streaming data services. So instead of running a Kafka cluster, which is quite a lot of work, try out if you can get away with Kinesis first. Now, this looks like a commercial here because I'm mentioning all of these AWS services here. But the truth is, our job is to take away the undifferentiated heavy lifting. You're not going to compete against your competitor on how well you can manage a database or how well you can manage a streaming service. you're going to compete about the service that you're implementing on top of that. And then you can take the advantage of letting somebody else run it for you in an automated way. Many more services you can try out here. Here's an example. The same customer that introduced DAX before, they used Amazon Elastic MapReduce to analyze their log files. And so they tried out using Amazon Athena instead, which is a service that allows you to run SQL queries directly on your S3 data. And the result was that the cost went down by 50% just by replacing Elastic MapReduce clusters with Amazon Athena. And the reason is that if you're running a Hadoop cluster, you have to wait until it's started up and it's running, and then you start crunching. And you get rid of that start time by using the Athena service. So the startup phase was the real money sink here, and they were able to get rid of it using Athena. And also the architecture now is a lot more simple and easier to administrate because there's less operations overhead. So the other takeaway here is instead of putting everything into a single database that does everything, you can now take advantage of different databases because they're also easy to administer. Don't have to do any administration here. So try to split up those use cases among different databases so you can leverage the good bits of each individual database. You can leverage all of the strengths of the individual databases. You don't have to compromise by putting everything into the same database. So you can, for instance, split up your application into pieces that use a NoSQL database, and then you can implement that on DynamoDB, or you can split up the other pieces that want SQL, and then you can differentiate between an OLTP system like Amazon Aurora or a data warehousing system like Amazon Redshift here. And that means try to pick the right tool for the job. You should be using something like DynamoDB or Cassandra or Mongo for key value databases. And then you can use a dedicated database for SQL, Aurora for online transaction processing, or Redshift, or something like Elasticache. So time to summarize now. Let's put it all together. Easiest way is turn off those unused instances. Make sure you automate as much as possible, and the simplest way to automate is by introducing autoscaling into your architecture. Use spot instances. Very easy to administer, now automatically supported by autoscaling. Consolidate with containers. And when you use serverless, Lambda, try to avoid those wait times that can be introduced by synchronous calls. Try to go as asynchronous as possible, and you can use step functions to do that. Cache everything. You should be becoming little hamsters that are caching all of the results and then avoid all the unnecessary work of recomputing those queries. And then be lazy and avoid reinventing wheels and administering everything on your own, and leverage those managed services. So with that, I'm looking forward to next year and seeing you all here again. Think about the optimization process. You can check out AWS Trusted Advisor to get some ideas on where you can save money, because Trusted Advisor, it will take a look at your architecture and highlight those unused instances. You can also check out the Well-Architected program. There is a whole pillar in Well-Architected with its own white paper for cost optimization. And if that isn't enough, here are the YouTube videos from previous talks at reInvent from the previous years, where Marcus and others are sitting together with me, sharing other tips and more ways of saving cost. I'm not going to highlight those repeats because we went through them already, but there are some other sessions you can see that are related to even more aspects of cost optimization. There's another one tomorrow on cost optimization tooling. So with that, thank you very much for coming, and I hope you save a lot of money.